So in 9.1b, we're adding and subtracting radical expressions. And this is going to be very similar to combining like terms, which you've done for a few years now. You can add and subtract radical expressions just like you would with like terms when we're looking at the variables. You have an example here. You can see here that 4x plus 2x have a matching variable with matching exponents. So they're considered like terms, and we can add them together. 4x plus 2x, we can combine that together and make it 6x. Same thing can be done with radicals if they are what we call like radicals. Okay? Like radical means that the radical itself is the same index. For example, square root and square root, or cube root, fourth root, and fourth root. It's very similar to the variables up here having the same exponent. For the radicals, they just have to have the same degree. I would not be able to add a square root with a cube root, but as long as they're all square roots, we're good. Okay? Then, the other thing that needs to be a match is the part inside. The radicand needs to be an identical match as well. So you have 4 square root of 7 plus 2 square root of 7. Those are like radicals. So I can add the coefficients in front, 4 plus 2, and just write that as a single radical statement. Just say 6 square root of 7. Okay. If the radicals do not match, square root of 5 and square root of 3, for example, it's very much like with terms that don't match. We just leave them next to each other. We don't add or subtract them. We just leave them side by side. Okay. So you have a couple of more examples here. You got 8 square root of 10 plus 5 square root of 10. Square root of 10s match. Those are like radicals. And so we can combine them together and do the 8 plus the 5. So the 8 and the 5 act as the coefficients. We can add them together and rewrite that as 13 square root of 10. Okay. Subtraction works the same way. On the right side, 10 square root of 7x minus 12 square root of 7x. These guys are a perfect match. So I can then take 10 and that negative 12 and combine them and get negative 2 square root of 7. If they're different, like the two bottom examples, 4 square root of 2 plus 8 square root of 3, then we don't add them or subtract them because they're not like radicals. We just make sure that each individual one is simplified, and that's as much work as we can do. So let's practice a few of these. The first 3 are pretty comfortable because they're already simplified. The radicals I can see here, square root of 5 and square root of 5, already match, first of all, and those are already simplified. 5 is not a perfect square, and it does not have any perfect square factors. But square root of 5 is a match to square root of 5, so I can combine these together. So I'll do the 2 plus 6, and I can rewrite this as 8 square root of 5. Same thing on number 2, square root of m, square root of m. Those are a match, so I can add these two radical terms. 3 plus 10 is 13 square root of m. On number 3, I've got a square root of 2y, square root of 2y, square root of 2y. These are all a match, so I can combine all of those. I'll start from the left and go right. So 7 square root of 2y plus another square root of 2y. You can think of this as having a coefficient of 1 in front if you don't see it. Those combine together to 8 square root of 2y. And then if I combine that with the third one, which is also a like radical, I really end up with 6 square root of 2y. And that is all simplified. Since they were all like radicals, I could add them all together. The catch, the more interesting part of this lesson, is the fact that sometimes we can't tell right away if something is a like radical because we haven't simplified it yet. So, if you look at number 4, we've got 2 radicals that at a glance appear to be different. But we will always have to simplify our answer anyway. So as we simplify, we may discover that we might have some hidden like radicals that we didn't know about because they weren't simplified yet. So look at what I mean on number 4. If you look at square root of 50, we did this one yesterday as well. We know 50 is not a perfect square, but we do know it's the product of 25 times 2. And so if we break that up, the square root of 25 separately to the square root of 2, then we know that that will be 5 square root of 2. Okay, that'll be a whole number 5, and then the square root of 2 will stay inside the radical. And then when we go to simplify the square root of 32, well, 32 again is not a perfect square, but it is the product of 16 times 2, which and separate out, so I can take the square root of 16 and leave the 2 inside. Move this over. And that lets us simplify this out to just 4 square root of 2. And so now we might ask ourselves again this time with the simplified versions, do we have like radicals? And the answer is yes, we do. And we can combine those together for a final answer of 9 square root of 2. So we were able to add those after all, but it was after simplifying that we could see that we had those like radicals in there. Let's try number 5. 27 is not a perfect square, but I do know 9 goes into 27 3 times. So I'll separate that. That's a perfect square, separate from the 3. And I'll take the square root of that because it is a whole number, so square root of 9 is 3. The other square root of 3 stays in. In the second term, 192 is a product of 64 times 3. And so if I separate that out, I get the square root of 64 times the square root of 3, and that gives us 8 square root of 3. And now that they're both fully simplified, I check to see, are they really like radicals or not? And in this case, they are. And so I can actually combine this all the way to a single radical term. 3 plus 8 is 11 square root of 3. Okay. On number 6, 20 is not a perfect square, but it is a product of 4 times 5. So if I separate that, square root of 4 times the square root of 5, I can take the square root of 4 and get a nice whole number and just leave the messier part inside the radical, just leave that as square root of 5. On the right side, 80 is a product of 16 times 5. And the square root of 16 can be separated out and evaluated. So the square root of 16 is 4 square root of 5 there. And now that I have these simplified, again, I get lucky enough here that I realize, oh yeah, these are like terms. I can combine them, 2 plus 4. I can write this as a single radical, 6 square root of 5. Oh, got a little bit weird there. Okay, let's go on to the next page. And so these are all just practice and exercises of that same concept. On number 7, I notice 4 square root of 5. That's already simplified. I can't do anything with that. 5 is a prime number, and it's not a perfect square, and we can't do anything with it. I can, however, simplify the square root of 200, because I can break that up into 100 times 2. Take the square root of 100 separately, and get 10 square root of 2. And that was being added to this guy here, which was 4 square root of 5. So I bring that down. And now they're both fully simplified. Again, I had to do that anyway, but now that they're fully simplified, I can really check, are these like radicals? Well, in this case, they're not. Even after simplifying, these are not a match, so I don't actually get to add them. This is really just the end of the road for this particular problem. Okay, so not like radicals here. So I did not add them. Okay. And then that would be our final answer. That would be as much simplifying as we can do for that particular problem. Let's take a look at number 8. We have 2 times the square root of 12 plus 6 times the square root of 3. 12 can simplify because I know there's a 4 in there. So I'm going to separate the 12 into 4 times 3. Separate the square root of 4 and the square root of 3. And the square root of 4 is 2. So what happens here? Well, this was multiplication, right? There was no addition sign kind of in here in the middle. It was just 2 square root of 12. That's multiplication. So when I am able to evaluate this, I got to realize, okay, so I had a 2 times whatever else was happening. Now it's 2 times 2 times the square root of 3. Okay? And when I do multiply that, this really all just cleans up to 4 square root of 3 on the left side. The other side was already simplified. I'll just bring this straight down. The other side was just 6 square root of 3, which couldn't be, simplified any further. And really the next question is just, do we have a like radical? And we do. And we can bring these together to just 10 square root of 3. Okay. Number 9, negative 3 square root of 5. That is as simple as it can get. But 162 is really the product of 81 times 2. And if I separate out the square root of 81, I'm going to get 9 square, oh, hello. Okay, I'm going to get 9 square root of 2. And then I can bring this guy down. That was being combined with negative 3 square root of 5. So now that they're both fully simplified, the question is, do I have like radicals? I do not. These are not a match, so I cannot take that any further. This is the end of the road because these are not like radicals. Just so you understand where that's coming from. Okay. On number 10, we just continue the process here. We're going to separate this out because I know 25 is a perfect square, but just a regular x is not. So that leaves me with 5 square root of x. On the other side, very similarly, I can separate out the square root of 16 and the square root of x. And that gives me 4 square root of x. And then I ask myself if these are a match, and they are. And I can write that as 9 square root of x. On number 11, 48 breaks up into 16 times 3, and then I have that times x as well. So I can take the square root of the 16, but I will not be able to do it for 3x. So when I take that square root, it'll be 4 square root of x. Sorry, 3x. Okay. On the other side, 192 happens to be 64 times 3 times x. And the square root of 64 can be separated out from the 3x. And that gives us 8 square root of 3x. And then we see that these are a match, and we finish out with addition here. So that gives us 12 square root of 3x. Okay. On number 12, 63 is not a perfect square, but I know 9 goes into that. So I'm going to separate that into 9 times 7 times the x, and take the square root of the 9, the factor that I can, and I'll leave just the part that I can't do inside the radical, which is a 7x. On the other side, I have minus 4 times the square root of 27x. Well, 27 is not a perfect square, but 9 goes in there 3 times, 9 times 3. Okay, so then I'll take the square root of the 9 separately from the 3x, and then the square root of 9 is 3, and then I'll have the 3x, and then negative 4 times that 3 will give us a negative 12. So I'll have 3 square root of 7x minus 12 square root of 3x, and because our radicals are not a match, this is as far as this goes. It is fully simplified, but I can't add it or subtract it. That's as much work as we can do on it. Okay. All right, let's check this one out. So we've got 2 square root of 75m. So 75 is not a perfect square, but I know 25 goes into that, so I'll break 75 up into 25 times 3, and then it still has the m. I'll take the square root of the 25 separately than the 3m. And that'll give me a positive 5 whole number that I'll now be able to multiply with the 2 that is now a whole number. So once that's a whole number, 5, I can then multiply those together. So I get 10 square root of 3m in that very first term. Okay, on number in the middle, 12 breaks up into 4 times 3 times m. And then I can take the square root of the 4 separately than the 3m. And the square root of the 4 is just 2. So that's 2 square root of, minus 2 square root of 3m. And then the last one, 108, I believe that is the product of 36 times 3m. And if I take the square root of the 36 separate than the 3m, then I take the square root of that and I get 6, just a minus, and then the square root of 36 is 6, square root of 3m. And then, of course, the question is, do we have like radicals? And in every one of these instances, the answer is yes. So then we can actually add those together. And 10 minus 2 is 8, minus 6 is 2. So this should give us just 2 square root of 3m as the final simplified equivalent to number 13. All right, on number 14. 48 is the product of 16 times 3, and then I have an A and a B. Both of those are power 1, so I can't do anything with them. The only thing I can take the square root of here is the 16 separately from that 3AB. That gives me 4 square root of 3AB. In the middle, that's already simplified. 3AB is already as simplified as possible. I can't do anything with it. So I'm just going to leave this as 2 square root of 3AB. And the last one is also fully simplified. 4 square root of AB. Again, AB I can't do anything with, so nothing I can do here. So this is just 4 square root of AB. And then I'll look to see if I have any like radicals. And in this case I do. Not all of them though. Only the first 2 are like radicals. They're both a 3AB radicand here and here. This one's not a match, right? So we're not going to combine that one. We'll only combine the first 2 together. 4 plus 2 is 6 square root of 3AB. The next one will just be separate and next to that because it cannot be added on. All right. Last one is a word problem, a little bit. It says find the perimeter of the triangle. Give your answer as a radical expression in simplest form. So just to review, remember perimeter is always just the sum of all sides together. Okay, so the perimeter is just the sum of all the sides. So all I have to do to find this perimeter is set up the sum of the 3 sides. One side is 5 square root of 7. The other one is square root of 28. And the last one is just 12. Okay, and the only one here that can be simplified is the middle term. So 5 square root of 7, I think we all feel good, is already simplified. Can't do anything with the 7. And 12 is just a whole number, so that's already simplified. But square root of 28 can break up into 4 times 7, and then I can take the square root of the 4 separate than the 7. So I get 2 square root of 7. And I'm adding that to 5 square root of 7 and the whole number 12. Okay, and then I notice that the 2 radical terms are like radicals, so I can add those. 5 plus 2 gives us 7 square root of 7. So our perimeter is 7 square root of 7 plus the whole number 12, and this is in centimeters. Okay, and if you wrote the 12 in front and the 12 plus 7 square root of 7, that would be perfectly acceptable as well. They're both equivalent. Just don't forget your units.